Here are the top 10 most important exponent rules that you need to know when working with powers. And before I show you the rules, let me give you a very quick reminder about what a power is. A power is just an expression that represents the repeated multiplication of a base by itself. And any power, let's say a to the power of n, is made up of two parts, a base and an exponent. So in this example, a is what we call the base of the power, and that just represents the number being multiplied repeatedly, and n is called the exponent, which represents the number of times the base is being multiplied by itself. So as an example, 2 to the power of 4 just means we have 2 being multiplied by itself 4 times. Or another way of saying that is that we have 4 factors of 2 being multiplied together. So in expanded form, this would equal 2 times 2 times 2 times 2, which is equal to 16. And now let's have a look at the rules you'll need to know in order to simplify expressions that involve powers. Must know exponent rule number 1, the product of powers. This rule states that if you have a product of two powers that have the exact same base, so let's say a to the power of m being multiplied by a to the power of n, you can actually simplify those into a single power by keeping the same base, so I'll keep the base of a, and then add the two exponents. So the new exponent would become m plus n. And now let me take you through a few examples so you can understand why this rule works and get comfortable using it. In this example, it says to write each product as a single power and then evaluate if possible. And then there are 3 examples here for us to try. Let's start with part A. I've given a bit more room for part A because I'm going to write it in expanded form so you can see why the product rule of powers works. 2 to the power of 3 just means 3 factors of 2 being multiplied together. And that needs to be multiplied by 2 to the power of 4, which just means 4 factors of 2 being multiplied together. And in this expanded form, I can see it's just repeated multiplication of 2 by itself. So I can write that in exponential form by making the base of the power 2, and then the exponent is just how many factors of 2 do I have being multiplied together. Well, I know there are 3 plus 4 factors of 2 in total. So my exponent is just 3 plus 4, which is 7. So my power becomes 2 to the power of 7. In this expanded form, 2 is being multiplied by itself 7 times, and 2 to the power of 7 is 128. So hopefully this was a good example for you to see why the product rule of powers works. When multiplying two powers together that have the same base, we can keep that same base and then add their exponents to get the new exponent on the power. And now let's do part B and part C without having to write it in expanded form. Let's just use this rule. In part B, I see I have two powers of 5 being multiplied together. When multiplying powers of the same base, I can keep that base the same, so I can keep the base of 5, and then I have to add their exponents. But I don't see an exponent on my first power of 5. If you don't see an exponent, there is an invisible exponent of 1 there. So to get my new exponent, I just do 1 plus 2, which means my new power is 5 to the power of 3, which is 125. And lastly, part C, I have two powers of x being multiplied together. Since the base of the power is a variable, we're not going to be able to evaluate, but we should be able to simplify it by writing it as a single power. Since the bases of the powers being multiplied together are both x, when using the product rule of powers, I know I keep that same base of x, and then to get the new exponent, I just add the exponents together, 7 plus 10, which means my simplified single power is x to the power of 17. Must know exponent rule number 2, the quotient of powers. This rule states that if you're dividing two powers that have the same base, so let's say a to the power of m divided by a to the power of n, you can simplify that into a single power by keeping the same base of a and then subtracting the exponents, m minus n. And then once again, let's do a few examples where you can see why this rule works and get comfortable using the rule. This example says that we need to write each quotient as a single power and then evaluate if possible. Notice in all 3 of these examples, we have a quotient of powers that have the same base. So we should be able to simplify them using this rule. But before I use that rule, let's have a look at part A, where I'll actually write it in expanded form so you can have a good understanding of how that rule works. 6 to the power of 4 just means 4 factors of 6 being multiplied together. And then 6 to the power of 2 means 2 factors of 6 being multiplied together. And then since 6 divided by 6 is 1, I can cancel that pair of factors, and then I can cancel another pair of factors of 6 as well. And now I need to figure out how I can represent this as a power. Well, it's still a repeated multiplication of factors of 6, so the base of my power will still be a 6. But how many factors of 6 do I have? Well, in the numerator, there were 4 factors of 6, so I can start my exponent off as 4. But then when I divided by 6 squared, that put 2 factors of 6 in the denominator, which canceled out 2 of those 4 factors that were in the numerator. So how do I show that I'm canceling out 2 of those 4 factors? I can just make the exponent 4 minus 2. And 6 to the 4 minus 2 is 6 squared, which communicates that here, what we have left is 2 factors of 6 being multiplied together, which is, of course, 36. And now that you can hopefully see why the rule works, where we subtract the exponents and keep the base the same, let's use that rule for part B and part C. In part B, we have 2 powers of 3 being divided. So what I can do is I can keep the base of the power as 3, but then subtract the exponents, 8 minus 4, which gives me a new simplified single power of 3 to the power of 4. And 3 to the power of 4 is 81. And then in part C, since the base of both powers is the variable x, I can use this quotient rule of powers, but I won't be able to evaluate it. When using the quotient rule, I keep the base of the power the same, it stays as x, but then I subtract the exponents, always doing the top one minus the bottom one, giving me 7 minus 4, which means my simplified single power is x to the power of 3. Must know exponent rule number 3, the power of a power rule. This rule states, if you have a power of a power, meaning the base of the power is a power itself. So let's say we have a to the power of m raised to the power of n. We can simplify that by keeping the base of the power the same and then multiply the exponents together. So then the new exponent becomes m times n. And now let's do a few examples so you can see how this works. In this example, it says simplify and evaluate where possible. So we'll simplify using this power of a power rule, but in part A, let me show you how it works by writing it first in expanded form. Having a 2 cubed squared means that we have 2 factors of 2 cubed being multiplied together. So I could just write this as 2 cubed times another 2 cubed. And then writing each of these in expanded form, each of those means 3 factors of 2 being multiplied together. And then from this expanded form, I can just see I have repeated multiplication of 2 by itself. So I can write this as a power where the base is 2, and the exponent needs to correspond to how many factors of 2 do I have here. So what I have is 2 groups of 3 factors of 2. So doing 3 times 2 will tell me in total how many factors of 2 I have, and 3 times 2 is 6. So my new power becomes 2 to the power of 6, which is 64. And hopefully this was a good illustration to you as to why this rule works. When we have a power of a power, we can just keep the base the same and then multiply the exponents together. And by multiplying the exponents together, it tells you how many factors of the base are being multiplied together. So let's now try and use that exponent rule for these 2 examples as well. In part B, I have 3 to the 4 cubed. Since it's a power of a power, I can keep the base of the power, 3, and then multiply the exponents together 4 times 3 to get my new exponent. So this equals 3 to the power of 12, which is a big number. 12 factors of 3 being multiplied together is 531,441. And then for part C, we won't be able to evaluate it since the base of the power is a variable, but we still can use the power of a power rule, which says we can keep the base of the power as x, and then get the new exponent by finding the product of those exponents, 7 times 4. And 7 times 4 is 28, so my simplified power is x to the power of 28. Must know exponent rule number 4, the power of a product. For this rule, if we have a power where the base of the power is a product of 2 factors, so let's say the base of our power is a times b, and the exponent is n. The rule tells me that what I need to do is apply that exponent of n to both factors of the base. So this would equal a to the power of n multiplied by b to the power of n. And then let's do a couple examples where we practice simplifying powers using this power of a product rule. For part A, I'll write it in expanded form so you can see why the rule works. It says that we have 3 factors of 2x squared being multiplied together. So let me write that in expanded form. And then because the order of multiplication doesn't matter, I could multiply all 3 factors of 2 together first, and then write all 3 factors of x squared beside each other after. And then simplifying this expression into exponential form, notice I have 3 factors of 2 being multiplied together. I could rewrite that as 2 to the power of 3. And then I have 3 factors of x squared being multiplied together. I could write that as x squared being cubed. And then notice what actually just happened here is we did the power of a product rule. This 3 got put as the exponent on 2 to make 2 cubed. And this 3 also got put as the exponent on the second factor of the base x squared to make x squared cubed. And then simplifying each of these powers, I know that 2 cubed, I could simplify that to 8. And then x squared being cubed, using the power of a power rule, I know I can keep the base of x, and then multiply the exponents together. 2 times 3 is 6. And now let's do part B a little bit quicker. Because the base of my power is a product of a 4 and an x to the 5, I know I have to apply this exponent to both factors of the base. I'll have to do 4 to the power of 2 multiplied by x to the 5 to the power of 2. And then simplifying each of these powers, 4 squared is 16, and then x to the 5 squared, using the power of a power rule, I keep the base of x, and multiplying these exponents together, 5 times 2, my new exponent becomes 10. Must know exponent rule number 5, the power of a quotient rule. For this rule, if we have a power where the base of the power is a quotient of values, let's say the base of our power is a divided by b, and we'll let the exponent be n, the power of a quotient rule tells me that that exponent of n has to be applied to both the numerator and the denominator of the base of the power. So this would become a to the power of n being divided by b to the power of n. And let's do a few examples to see how this rule works. In this example, it says to simplify and evaluate where possible. All 3 examples, we have powers where the base of the powers are all quotients. So we'll use the power of a quotient rule for all of them. But when doing part A, let's start by writing it in expanded form so you can see how the rule works. 3 over 4 to the power of 2 just means we have 2 factors of 3 over 4 being multiplied together. And then I could combine these into a single fraction just by multiplying the numerators, 3 times 3, and dividing that by the product of the denominators, 4 times 4. In the numerator, notice it's just 2 factors of 3 being multiplied together. I could rewrite that as a power, 3 squared. And then same thing in the denominator, I could rewrite that as 4 squared. So notice what we did was we used this rule. We just took the exponent and applied it to both the numerator and denominator. This 2 got put as the exponent on the 3 and the 4 to give me 3 squared over 4 squared. And then we should simplify that. That would simplify to 9 over 16. And now that you can see how the rule works, let's do part B and C. Part B, since the base of the power is a quotient, I know I have to put that exponent of 3 as the exponent on both the 2 and the 5, giving me 2 cubed over 5 cubed, which is just 8 over 125. Part C will be a little bit trickier. It's still a power of a quotient, right? The base is a quotient, but in the numerator of the quotient, I have a product. So I'm going to have to combine the power of a product and the power of a quotient rule here. Let's start by using the power of a quotient. This exponent of 2 has to be put as the exponent on the numerator and denominator. But be careful, when I put it on the numerator, make sure I put that 3x to the power of 5 in brackets, showing that whole numerator is being squared, over that 7 is being squared as well. And now I do my power of a product rule, where this exponent of 2 has to be applied as the exponent on both factors of the base. I have to put it as the exponent on the 3 and on the x to the 5. And then I'll make a bit of room so I can simplify these powers. 3 squared is 9. X to the 5 squared. For the power of a power rule, I keep the base of x, and then multiply the exponents together. 5 times 2 is 10. And that's being divided by 7 squared, which is 49. Must know exponent rule number 6, the zero exponent rule. This rule states that any number to the power of 0, so let's say a to the power of 0, is equal to 1, as long as the base of the power, a, is not 0 itself, because 0 to the power of 0 is undefined. And this will be an easy rule for me to show you how it works with a couple quick examples. Starting with example 1, I just want to evaluate 5 to the power of 0. Well, anything to the power of 0 is 1, so I know this is equal to 1. And then in example 2, I made up an example that I think will illustrate to you why something to the power of 0 is 1. Notice that the numerator and denominator are the exact same. They're both 2 to the power of 4, and anything divided by itself has to be equal to 1. So for that reason, I know that this expression, it must equal 1. Keep that in mind, and let's go ahead and use the quotient rule of powers to simplify this expression. When dividing two powers that have the exact same base, I know I can keep the base the same and then subtract the exponents, 4 minus 4. Making this equal to 2 to the power of 0. And since in the original expression it's something divided by itself, I know that has to equal 1, meaning 2 to the power of 0 has to equal 1. And that's it for the zero exponent rule. Must know exponent rule number 7, the negative exponent rule. There are two versions of this rule that I want to show you. Rule number 1, if you have a base a raised to a negative power, that's equivalent to the reciprocal of that power raised to its positive exponent. So that would be equal to 1 over a to the power of positive n. And then a second version of this rule, which is equivalent, but a different way of thinking about it for when you have a power where the base is a fraction. If you have a power where the base is a over b, and that's raised to the exponent of negative n, that's equal to, you take the reciprocal of the base, meaning you do 1 over it, or flip it, making it b over a, and then make the exponent positive. And then with a few examples, let me show you how this rule works. In this example, it says simplify and evaluate where possible. So let's go through all 4 of these examples. In part A, we have 5 to the power of negative 2. And to simplify a power, we need to get rid of any negative exponents. And I can do that by using this rule up here. Any power that has a negative exponent, I can just write its reciprocal with a positive exponent. So this would be equal to 1 over 5 to the power of positive 2. And 5 squared is 25, so this equals 1 over 25. And then in part B, I can use this rule, which is kind of like a shortcut of this version, for when the base of the power is a fraction like we have in part B. Because the exponent is negative, what I can do is write the reciprocal of the base of the power, which means flip it, making it 3 over 2, and then change the exponent to positive 3. And then using my power of a quotient rule, I know I have to raise both the numerator and denominator to this exponent of 3, making it 3 cubed over 2 cubed, which is 27 over 8. And then in part C, I have a quotient of powers that have the same base. Using my quotient of powers rule, I know that I can write that as a single power by keeping the same base and then subtracting the exponents, 4 minus 6, making this equal to x to the power of negative 2. And then to simplify this so it doesn't have a negative exponent, I write its reciprocal with a positive exponent, so 1 over x to the power of positive 2. And to understand why x to the negative 2 is equal to 1 over x to the positive 2, maybe if I wrote this in expanded form, you would understand. I'll just do that down here really quickly so you can see. In the numerator, I have x to the power of positive 4. That's just 4 factors of x being multiplied together. And then the denominator is 6 factors of x. And then since x divided by x is 1, I can cancel 4 pairs of x's out, leaving me with, in the denominator, 2 factors of x, and x squared. And then in the numerator, I have a 1, because all 4 of those factors of x divided by all 4 of those factors of x is equal to 1. Now let me erase this so we have room to do part D. In part D, we're going to have to combine pretty much all of the exponent rules that we've learned so far. Let me start by simplifying the numerator. I can multiply these constant factors together. 2 times 3 is 6. And then I can multiply my powers of a together. That first power of a, even though I don't see it, it has an exponent of 1 on it. And when multiplying powers with the same base, you keep the base the same and add their exponents. So it becomes a to the 1 plus 3, which is a to the 4. And then multiplying my powers of b, b to the 4 times b to the 2, keep the base of b, add their exponents, 4 plus 2 is 6. And now into the denominator, I can use my power of a product rule to simplify this. This exponent of 2 has to be applied to all factors of the base. So I have to do 2 squared, which is 4, and then a to the power of 3 squared. If I multiply the exponents using my power of a power rule, that's a to the power of 6. And then b squared to the power of 2, multiply those exponents, I get b to the power of 4. And now I can do all of my divisions. I'll start by looking at the constant terms. I have a 6 divided by 4. That can reduce. 2 goes into both 6 and 4. It goes into 6 3 times and into 4 twice. And then I'll look for powers that have the same base and then use the quotient rule of powers. I have an a to the 4 being divided by an a to the 6. Using the quotient rule of powers, I keep the base of a and then subtract their exponents. 4 minus 6 is negative 2. And then I have 2 powers of b being divided, keep the base of b, and then subtract their exponents. 6 minus 4 is positive 2. Notice when I was dividing those powers, I made sure to put the quotients up in the numerator. And now if I have any powers with negative exponents, I need to express them as powers with positive exponents using the proper negative exponent rule. So let's have a look at this a little bit more carefully, and I'll show you how we can think of this. This a to the power of negative 2, I can't have a negative exponent in the final answer. So what we would do, we would take that power of a to the negative 2, we can think of it being multiplied by that entire fraction. And now using my negative exponent rule, I can replace a to the power of negative 2 with the reciprocal of that power with its positive exponent. So 1 over a to the power of positive 2. And then multiplying these fractions, you can see that this a squared is just going to move into the denominator with the 2. And then multiplying 3b squared by 1 isn't going to change it. But instead of doing all of those steps to get rid of that negative exponent, there's a shortcut. Let me backtrack and show you. If in your final answer you have any powers with a negative exponent, so this a to the negative 2, you can take that power and move it to the denominator of your fraction if you change the sign of its exponent. And that's it. There's that same final answer. Must know exponent rule number 8, the rational exponent rule. For this rule, I just want to show you how we can rewrite powers that have rational exponents. If you have b to the power of m over n, we can actually rewrite that or think of that as the nth root of b raised to the power of m. Or equivalently, it's the nth root of b to the exponent of m. So notice for this rule, whatever the denominator of the rational exponent is, that becomes the index of the root. And then the numerator of the rational exponent becomes the exponent on the base of the power in the radicand, or as the exponent on the outside of the root. Now there are restrictions on when this type of power is defined, but we'll cover that in the last section of the video. For now, let me just show you a couple quick examples so you can see how we can work with these. All right, let's work through all 3 of these examples and try and simplify them and evaluate where possible. In the first example, noticing that this seems to be in this structure, I could rewrite it in this format right away if I wanted to, by changing it to 8 to the power of 2 over 3 would be the rational exponent. Right, the index of the root becomes the denominator of the rational exponent. But I don't think writing it this way makes it easier to evaluate. If we look at just the base of the power, we have the cubed root of 8, and on that 8, there is an exponent of 1 on it. So if I wanted to, I could just rewrite this, which is this format, as a power with a rational base, where I make it 8 to the power of, I take this 1, make it the numerator of the rational exponent, take this 3, and write it as the denominator of the rational exponent. So it's 8 to the 1/3 squared. And based on the power of a power rule, you can see why this is equivalent to what I wrote first, 8 to the power of 2/3. But I chose to write it in this format just to show you that if you see 8 to the power of 1/3, that means the same thing as the cubed root of 8, which just means what number multiplied by itself 3 times is 8? Well, 2 times 2 times 2 is 8, which means 8 to the power of 1/3, the cubed root of 8, is 2. So since this is 2, I now need to do that squared. And 2 squared is 4. And then moving on to example 2, I see I have a fraction raised to a negative exponent. The rule we learned in the last section was that I can make this exponent positive if I write the reciprocal of the base. So it would become 81 over 49 raised to the power of positive 3 over 2. And then I have to raise both the numerator and denominator to this exponent of 3 over 2. And I can rewrite both of these powers. Based on my understanding of the power of a power rule, I could rewrite 81 to the power of 3 over 2 as 81 to the power of 1 over 2, all raised to the power of 3. right? When multiplying 1/2 times 3, it's equal to 3 over 2, which is why this term is equal to that term. And then doing the same thing for the denominator, I now have an expression that's a lot easier to evaluate without a calculator. 81 to the power of a half and 49 to the power of a half. If I wrote those in a format you're probably more familiar with, if I wrote those powers with rational exponents in this format, the index of the root symbol would be 2 in both of these scenarios. And that's just the square root of 81 and the square root of 49. When the index of a root is 2, you don't actually have to write them. And you know what the square root of 81 and the square root of 49 means. It just means what number multiplied by itself is 81, that's 9, and what number multiplied by itself is 49, that's 7. So I can replace that root 81 and that root 49 with 7. But let me start by making a bit more room so I can do that. So I know what I have here is a 9 being cubed, which is 729. And what I have here is a 7 being cubed, which is 343. And then lastly, with example 3, I want to simplify that expression. I have a power here, so I'll keep the base of m and then multiply the exponents, making it m to the power of -6. And beside it, I have the square root of m to the 4. I don't see an index with the root symbol, so I know the index is 2, which means I could rewrite this. Based on this rule here, I could rewrite it as a power with a rational exponent. It would become m to the power of 4 becomes the numerator of the rational exponent, and the index 2 becomes the denominator. So it's m to the power of 4 over 2. And 4 divided by 2 is just 2. And this is divided by m. And then I have the square root of p times q to the power of -3. Using this rule, I can write them both as powers with rational exponents. On the p underneath the square root symbol, there's a 1, and the index of this root, even though we don't see it, it's 2. So this power of p becomes p to the power of 1 over 2, and this q becomes q to the power of -3 over 2. And now I just have to simplify this. I have an m to the power of -6 times an m to the power of 2 when multiplying powers with the same base. I keep the base the same, and then add the exponents. -6 plus 2 is -4. And that's being divided by an m to the 1, so I might as well simplify that now as well. When dividing powers with the same base, we keep the base the same and subtract the exponents. -4 minus 1 is -5. And then in the denominator, I also have these powers of p and q. But for my final answer to be fully simplified, it shouldn't have any negative exponents. So I'll take this power that has the negative exponent, move it up to the numerator, and that will change the sign of its exponent. And this power of m that has a negative exponent, if I take it and move it down to the denominator, I can change the sign of its exponent as well. And there's my final simplified answer where all of the powers have positive exponents. Must know exponent rule number 9, the equality of exponents rule. This rule is going to come in handy when you're solving exponential equations. Let's say you have an equation where you have two powers with the same base set equal to each other. So for example, what if we have a to the power of m equal to a to the power of n? Because these powers have the same base, the only way they could be equal to each other is if the exponents are also equal to each other. Which means if a to the m is equal to a to the n, we would know that m has to be equal to n. So let me go ahead and show you an example of when we would want to use this rule when solving an exponential equation. If you have this exponential equation where you're trying to solve for the value of the variable x that makes the equation true, if you can rewrite these two powers so that they have the same base, we would be able to use this rule where we could then set the exponents equal. Well, 25 and 5 could both be written as powers of 5. 25 is the same thing as 5 squared. And on the right side of the equation, it's already a power of 5. It's 5 to the 1, but I'll just write it as 5. And let me simplify this power of a power that I have on the left by multiplying the exponents together. So the base of the power is 5. And when I do 2 times x minus 1, make sure I multiply the x and the -1 by 2 to get 2x minus 2. And that's equal to 5 to the power of x plus 4. Now that I have an equation where I have a power equal to a power where the bases are exactly equal to each other, I know the only way this equation could be true is if the exponents were also equal to each other. So I can just set the exponents equal. 2x minus 2 must be equal to x plus 4. And then I just solve this equation. I'll bring the variable terms to the left, and the constant terms to the right, and I figure out that x is equal to 6. And you could check this answer in the original equation, subbing it into both the left and right side, and make sure you get left side equal to right side. And the last section of this video, I want to go over some restrictions on powers. All of these powers we've been working with, they're only defined for certain values depending on what the base and the exponent of the powers are. So let's go over 3 different scenarios. For this power, a to the power of n, we're going to look at 3 scenarios for the value of a. If a is equal to 0, if a is greater than 0, and if a is less than 0. And then for each of those scenarios, we'll look at what values of the exponent, n, make the expression defined and which make them undefined. Well, if we have a to the power of n where a is 0, that just means we have the power 0 to the power of n. That's going to be equal to 0 if the exponent n is greater than 0. So for example, 0 to the 1, 0 to the power of 2, 0 to the power of 100, or 0 to the power of any positive number is going to be equal to 0. But it's undefined if the value of the exponent is less than or equal to 0. Right, 0 to the power of 0 is undefined, but so is 0 to the power of any negative number. That's undefined. Well, why would 0 to the power of negative 5 be undefined? Well, based on the negative exponent rule, that'd be 1 over 0 to the power of positive 5, which is 1 over 0, and we know we can't divide by 0, so that's undefined. All right, how about a to the power of n when the base of the power a is greater than 0? That's easy. If the base of the power is greater than 0, then the power is defined for all values of n. So basically, if you make the base of your power any positive number, let's say 2, you can make its exponent any real number and you'll be able to get a value. You can make it 3.1. You can make it 2 to the power of negative pi. It wouldn't matter. As long as you make the exponent any real number, the power will have a value. But the third scenario is where things get a little bit tricky. What if the base of our power is less than 0? So for example, what if we have negative 5 to the power of n? For what values of n is that defined, and for which ones is it undefined? Well, it's defined for all integer values of n. And remember, the set of integer values are the positive and the negative whole numbers. So like negative 2, negative 1, 0, 1, 2, and so on. So if you make the exponent on a negative base, any integer, it'll have a value. But a power with a negative base is actually undefined if the exponent is any irrational number. So for example, negative 5 to the power of pi would be undefined because pi is irrational. So we know it's defined for integer values, undefined for irrational values. Well, what about rational values? Well, the answer to that is it depends. If the exponent n is a rational number, let's say b over c, the power will be defined if c, the denominator of the rational exponent, is odd, but it'll be undefined if c is even. And now let me take a shot at explaining to you why this is the case. Let me write down 2 powers for us to think about. The first power, negative 4 to the power of a half, that just means the square root of negative 4, which means what number multiplied by itself is negative 4. Well, any number, when you multiply it by itself, it's going to become positive, right? 2 negatives multiplied together is positive, 2 positives multiplied together is positive. So there's no way I can multiply a number by itself and get negative 4, which is why this power is undefined. And whenever this denominator is even, we're going to be looking for an even number of factors multiplied together to get a negative base, and that's just not possible. Which is why all powers that have a negative base and a rational exponent where the denominator is even is going to be undefined. But if the base is negative and the rational exponent has an odd denominator, for example 3, we'd be looking for 3 factors of what equals negative 8. Well, 3 factors of negative 2 equals negative 8. So the answer to that is defined. It's negative 2. And anytime we have an odd denominator in the rational exponent, we're looking for what number multiplied by itself an odd number of times is a negative value, which is always possible, which is why these powers are defined when the denominator is odd. So let's end off this video where I'll write down a bunch of different powers, and let's see if we can circle all of the powers that are defined. So out of all 10 of these powers, let's figure out which ones are defined. First of all, I know if the base of a power is greater than 0, it's going to be defined for all possible values of the exponent. So I know that 2 to the power of 4, 6 to the power of pi, 5 to the power of 3 over 2, those are all going to be defined because their bases are all positive. It doesn't matter what their exponents are. And now let's look at the 3 powers that have bases of 0. If the base is 0, I know it's going to be defined if the exponent is greater than 0. So that's only this one right here, 0 to the power of 3 over 7. That will be defined. But 0 to the power of 0 and 0 to the power of negative 4 are both undefined. And now let's look at the 4 powers where the bases are negative. Well, if the base is negative and the exponent is an integer, it'll be defined, which means negative 2 to the power of negative 3 is defined. But if the exponent is irrational, it'll be undefined, which means negative 7 to the power of root 2. Root 2 is an irrational number, so this power will be undefined. And that just leaves these 2 powers. They both have a negative base with a rational exponent. This one has an even denominator in the rational exponent. This one has an odd. When it's a negative base with a rational exponent, it's only defined if the denominator of the rational exponent is odd, which means negative 3 to the power of 5/3 is defined, but negative 3 to the power of 5 over 2 is undefined. So hopefully this video made you really understand and think about how powers work and how to use all of the rules that go along with them. Make sure to leave a comment about what you want to see a top 10 about next.
Jensen